Hi guys, thanks for tuning in. In this video, I'm going to talk a little bit about modeling and simulation. In particular, I'm going to help you guys through two assignments that you'll see in Schoology. We have this dice roll algorithm and this dice roll simulation. I'm going to try to structure this video in such a way that you could decide how much help you want on each of these assignments. So theoretically, these are both assignments that you should be able to complete just using the stuff we learned in our first couple notebooks: Python basics, data structures, modules, packages, and distributions. Particularly data structures is going to be very helpful for these two notebooks. However, what I'll do is I'll structure the video such that if you don't want a lot of help and you kind of get the idea, you could pause the video and go ahead and do this algorithm and the simulation on your own. And then if you get stuck or you want a little bit more guidance, you could go back to the video then and press play, and there will be some more direct help with how to do these assignments. But first, I don't feel good about doing a simulation with you guys unless I talk about what modeling and simulation are, why scientists use it, and why Python is particularly good at modeling and simulation. So I'm not going to do this entire set of notes. These are for after spring break, but I'm going to do the first couple slides just to motivate what we're doing here. So scientists usually want to better understand some sort of phenomenon that's occurring in the natural world or some sort of phenomenon that's occurring in human society. And one way that scientists get a handle on a phenomenon is by setting up an experiment. They use the scientific method and a real-world experiment to record data and analyze that data and get a handle on that phenomenon and what might be causing it. There are certain situations, though, where setting up an experiment can be really costly, maybe it's just very impractical, or it might even be unethical. And so simulation is a way for scientists to simulate a phenomenon that's happening in the real world, try to understand it better without the cost or unethical nature that would come with an experiment. And I have some examples for you. So here's a costly experiment. You might read some stuff in the news about universal basic income, and so a scientist might say, yeah, what would happen, let's say, to the blood pressure of Americans if everyone was given a universal basic income of $15,000? And that's a valid research question. Scientists might want to know the answer to that. If people had to worry less about their income, would that lower their stress levels and then therefore lower their blood pressure? Maybe. Maybe not. Maybe you just wasted $15,000 in terms of health outcomes. The best way to find out would be to run an experiment. Unfortunately, running such an experiment would be pretty darn expensive, because if you have an experimental group of several hundred or several thousand people, you're giving $15,000 to several hundred or several thousand people, which adds up very quickly. So it might be a good experiment, but maybe most researchers can't afford to run that experiment. Also, some experiments would be impractical. So you might have a research question of what would better help relieve traffic congestion in New York City: building a new bridge from New Jersey to New York, or building a new tunnel, because tunnels and bridges usually have different traffic patterns. One way you could do it is you could build both, and you could open one up for a year and then close it, and then open the tunnel up for a year and then close it, and then compare the bridge and the tunnel data. Well, that's not very practical. First of all, because now you have a bridge and a tunnel, so you might as well open both of them. But also, you just spent a lot of extra money. What are you going to do? Like destroy the bridge because the tunnel was better? Then at that point, you might as well have just kept both of them. So that was not a practical experiment. Though you could run computer simulations of that, and you could simulate traffic patterns in New York, and you could simulate the traffic pattern with an extra bridge versus simulate the traffic pattern with an extra tunnel, and then you could get an idea of what you believe to be the better path based on those simulations. We'll talk more about that in a minute. And then it's also possible that your experiment could be unethical. Now, this one's ridiculous. No one would actually want to run this experiment, but this would be an unethical experiment. What happens to a person's liver if they drink nothing but Monster Energy drinks for a month? Well, I'm not sure what happens to that person's liver, but if you believe that an experiment might damage someone's liver, then it would be unethical to run that experiment. Now, I don't know if you could really make a computer simulation. Well, you actually probably could, actually. It would be more ethical to simulate what would happen to a person's liver function based on all of that sugar and caffeine than it would be to run that experiment in the real world. And that introduces the idea of modeling and simulation. So we'll go into these slides in more depth next week, but the idea with modeling is that a model serves as a simplified digital representation of some real-world phenomenon or scenario that you're trying to understand better. And then once you have a model, simulation is using that model to gain insights about the real-world phenomenon, usually by running the scenario over and over and over again and looking at the accumulated effect of that model. So a simulation would be running it over and over and over and over, running the model over and over and over again and looking at those results. So, for example, I talked about it on the previous slide, but it's not practical to build a bridge and a tunnel to New York City and then see which one's more effective at reducing traffic. But simulation would be practical, right? Running two different traffic simulations, people run traffic simulations all the time. So you run one simulation with a new bridge, then run a different simulation with a new tunnel, and then from that comparison, you can make an educated, informed guess about which of the two decisions would be better for New York City. Now, you do have to remember, though, you're getting an insight about the real world, but that traffic simulation is not the real world. It's a simplification of the real world. So, it doesn't consider every possible variable, every possible scenario. What you're getting is an indication about what might be the best path forward, but you're not necessarily getting a definitive answer. But in this case, it's the best you got because you're not building the bridge and the tunnel. So creating a traffic model of New York City and then running a simulation with the bridge versus a simulation with the tunnel, that's going to be your best way to make an informed decision going forward. And that's the idea of modeling and simulation. And then we'll talk about, after spring break, some other cool things we can do with simulations. But I'm going to end the notes right here. And I'm going to say that the reason this relates to what we're doing today is we want to run a dice roll simulation. And we are going to roll a die 1,000 times. Well, I could have brought a bunch of dice to class and had those handed out, and you guys could have rolled a die 1,000 times and looked at the results and graphed those results. But that's not practical because, you could roll a die 1,000 times during a class period, but it would be very boring. It'd be hard to keep track of all the data. People would probably not want to spend their class period doing that. So instead, we're going to do a simulation. We're going to create a model of a die using the randint method in NumPy. And then we're going to run a simulation, which is going to be rolling that die many, many times. And then we're going to graph the results and see what it looks like. Now, it's not going to be very interesting because you kind of know ahead of time basically how the results are from rolling a die 1,000 times. There's 6 faces to a die, and you know that each face is equally likely. So, if the simulation goes as planned, you'll have approximately the same number of 1s, 2s, 3s, 4s, 5s, and 6s, up to some variance, because, you just have some random variance when you're rolling a die. So it's not perfectly uniformly distributed on a small number of rolls like 1,000, but it'll be pretty darn close. All right. So that is the idea behind all of this. Now, we have this dice roll algorithm. For this assignment, it's not due until Wednesday, March 30th. I think most of you guys could get it done in class today. It doesn't take very long. You're going to open up a blank notebook in Notability, and you're just going to write in plain English how you would simulate rolling a fair die 1,000 times and how you'd record that number that appears on each face of the die and how you would display the results graphically. Now, the reason I think this will be a pretty quick assignment for you, the secret to this assignment is what you need to do is pretty much laid out in this dice roll simulation notebook. So If you look at the next assignment in Schoology, the dice roll simulation, if you download this notebook and put it into your folder, so I'm working out of period 6 now because my period 4 folder is starting to get kind of cluttered. By the way, if you feel like your notebook is also, or your folder is also starting to get cluttered, you can make some subfolders, right? So, I could call this dice roll simulation. And then I could drag and drop this into that folder, and you could do that with all of your different notebooks, just so everything's kind of organized. I'm not going to do that right now, but you certainly can if you'd like to. But anyway, once you have this dice roll simulation notebook sitting in your Python folder, then you can launch that notebook in Jupyter. There we go. And honestly, the algorithm is kind of described in these bullet points. So the first thing we need to do is randomly generate dice rolls. So you could write about how you're using NumPy's randint method to generate random numbers between 1 and 6, because those are the values of the faces of a die. And then the way we're going to roll the die 1,000 times is, remember that the randint method in NumPy specifically, this version of the randint method, allows you to repeat the experiment as many times as you want. So you're going to put your indices here for the faces of the die that you want, and then you're going to put a third parameter here, a third argument here. You're going to replace this parameter with the number of times you want to repeat the experiment, which will be 1,000. That'll roll the die 1,000 times, and that'll give us a NumPy number array with 1,000 dice rolls in it. Then we're going to use another method we learned about in a previous notebook, the NumPy bin count method. Now, I put some documentation for each of these methods directly into the notebooks. If you want to read more about NumPy's randint method, you could click here, and you can read all about how the randint method works in NumPy, and you can even see some nice examples. Bin count. That's going to be a function that will go through all 1,000 dice rolls, and it will look at the 1s through 6s, and it'll just kind of lump them together. I got 50 1s, I got 75 2s, I got 63 3s, whatever. So it gives you an array with a count for how many times they appeared, and you can see how, they have an example of the bin counter here in this documentation, so you can read all about how this function works. Reading documentation is part of being a Python programmer. And then for making your histogram, same idea. We have code. Actually, the notebook, the algorithm doesn't necessarily say how you should visually illustrate the results, right? It just says display the results with the frequency of each number graphically. That's called a histogram, though. So in the dice roll algorithm, when they say display the results, the hope was that you read that and you're like, oh, well, the best way to display this would be a histogram, because a histogram is a graph of the frequency of each occurrence. But this notebook gives it away. It tells you specifically here, this is a histogram. And so you can read about, we'll do a random coloring for our histogram, and then I should have had a link here also for PyPlot, how to plot a histogram, but we did that in a previous notebook. So the idea with this histogram would be to go back to a previous notebook that we did as a class and use that code for a histogram and kind of copy paste change for our scenario. All right, so this is a good place for you to pause if you think you're ready to write up your dice roll algorithm, because really, you're just kind of summarizing what you see in this notebook. Similarly, some of you guys might want to pause right now and just do the dice roll simulation without me. The intention is for you to do this without me, but also the intention is for me to be in class so I could walk around the room, give people advice, kind of help you get started. Since I'm not in class and I'm not able to do that right now, what I'll do in a minute is I will help you code this and do this a little differently than I usually do in a typical school year. But I think there's going to be a large number of you guys that would prefer to pause right now, look at previous notebooks, and try to do these 3 tasks. These are essentially homework tasks, right? You might want to try to do those without the guidance of a teacher. So feel free to do that. Otherwise, what I'm going to do right now is help you code this out. Please don't do this with me immediately, though. Like, you should at least try these on your own, because you're going to be doing simulations on your own next after spring break. So first of all, I'm going to import NumPy. A common thing for Python programmers to do is to rename the module something shorter. NumPy, people often name it, excuse me, name it NP for NumPy. So I'm going to import NumPy. Now I'm going to make a num array that's going to represent my dice rolls. So I'm going to do np.random.randint. So I'm using the randint method of the NumPy module. Now I'm putting 1 to 7 here. I'm not going to be done. I'm just giving an example here, but I'm going to put 1 to 7. And the reason is that randint is exclusive on the right endpoint. So this will actually give me a dice roll between 1 and 6. So if you run this a bunch of times, it's like rolling a die. I rolled a 5. I rolled a 3. So the more you shift enter, the more you can see your different dice rolls. And you'll notice that these will always be between 1 and 6. Now, it'd be very boring to shift enter 1,000 times and, on a separate sheet of paper, write up all these dice rolls. Especially because we have the ability here to just put a 1,000 in there, and it'll give me all 1,000 dice rolls as a single NumPy number array. Look at that. I just did. So this is kind of our model. Getting a random integer from 1 to 7. This is a model of a die. And then, to make it a simulation, you put the 1,000 in here, because a simulation is running your model numerous times to aggregate the data and see on the aggregate what are the results of the experiments. So the model is going to be randint from 1 to 7. The simulation is allowing it to go up to 1,000 dice rolls, and then we'll use a bin counter to count up those results. All right, so that's the first section done. By the way, if you do read the documentation, you'll notice that you could write size equals in front of the 1,000. The newer version of NumPy prefers that you put size equals 1,000 here, really just to give more description to what this 1,000 is, so that other people reading your code will read this and be like, wait, what is this 1,000? Like, what's this extra argument here? Oh, it's the size of the array that we want. How many times we want to repeat this experiment. So honestly, if you want the best version of this, put a size equals 1,000 in front of your 1,000. It'll run either way, though. This is the old version. This is the newer preferred notation. All right, so we have 1,000 dice rolls. By the way, every time I've shift entered this, it's been changing. So it's a new simulation every time. All right, then let's move on. And let's do a little bin count here. So again, the intention here would be for you to look at previous notebooks and for you to look at this documentation and write up this code yourself. But I'm going to help you guys through it if you need it. So if I want to count up the rolls, I'm going to use the NumPy module, and I'm going to use the bin count method of the NumPy module, and I'm going to pass it my number array, and I can print my count. Okay, so when I rolled my die, I rolled 0 zeros. Bin count, if you look at the documentation, it's going to start counting at 0. Well, when you roll a die, you won't roll any zeros because there is no 0 on the face of a die, so it's 0 there. But I rolled 170 ones, 179 twos, 158 threes, so on and so forth. And you can see it doesn't look perfectly uniform. It's not the same number for each of them, but you wouldn't expect rolling a die to give you exactly the same number. It's just roughly the same number of rolls. That's why playing a board game where you roll a die is interesting, because, over a large number of rolls, this will start to become more. These numbers will start to become more and more packed together. But there is some variance. Otherwise, a board game would be really boring if everything, if there was never any random variance. All right, I'm going to write a short little for loop here, just for our own sake. For I in range 6, I'm just going to print out a little descriptive string. I'm going to say the number of space plus, I'm going to parse a string here with I plus 1 in it. And then put another quote. Just put a space here. You can probably see what this string's going to look like. And then I'm going to parse one more string. I'm going to go into count roles. I'm going to extract out the I plus first element. And I think if I run that, it should be good. Yeah, here it is. So what it's doing is, for each of these possible dice roll values, it's going to print the number of ones is, and then the number of ones, and then the number of twos is, and then the number of twos, because it's just getting the value out of count rolls here. So it's just extracting those values from this array. Okay, so the number of ones is 170, the number of twos is 179, so on and so forth. That's kind of optional, but it's nice to have. All right, and then finally, you need to create a histogram. And typically, when you're creating a histogram like this, you're probably copy-pasting from a histogram that we did previously. So let's look. I think I did this out of my Chapter 4 folder, and I believe that this would have been in data structures. Could be wrong, but I'm pretty sure this was in data structures. Nope, I'm wrong. Must have been, oh yeah, it was in modules, because I was telling you guys how to use PyPlot. So let's open up modules. But you guys will do the same thing. You open up old notebooks, look for the stuff you've coded in the past. Yeah, here it is. We have this, fairly nice histogram. So I'll paste this in here. The plan will be to use that. Now, I remember I improved it. So let me take this improved version and I'll use that. All right, so we're starting with that as a basis. Now, you gotta update your comments as necessary. We have to change things as necessary. For example, these bins don't make any sense for a histogram of dice rolls. Because when you're rolling a die, it's a 1, 2, 3, 4, 5, or 6. If you're rolling a 100 on your die, you must have a very different, your dice might look very different than the ones we're talking about here. So we're gonna have to update stuff, but the beginning's the same. Import matplotlib as plot. This is a line of code that allows us to put a graph in line. You know what? I'm going to create an array of colors. We're going to make this fun. So I'm going to make a color array. This is really just to randomly color the plot each time we run it. So blue, red, green, yellow. Just an array of random colors just for fun. My bins, I think, are to be 1, 2, 3, 4, 5, 6, 7. Actually, it might just work to 6, but I'm going to leave it at 7. For some reason, I have 7 in my key, so we'll try that. Now, nums 50, I don't have nums 50. That was the previous notebook. I have num array. Num array is the array that's storing all of these dice rolls. So you better, you have to change these variable names. You have to pass the right argument here. Okay, so bins is 1 through 7, so that's going to be fine. Align mid, good. What I'll do next here, I want to do something kind of fun. Instead of locking this in at a single color, I'm going to use numpy.randomChoice. And I'm going to take out a random choice from this color array I created. Is this a necessary part of this algorithm? Not really. I mean, it's just to make it more visually interesting. Each time I run this code, I'm going to get a different random choice from this color array. Okay, I've got my edge color is black. In my key, I coded black a little bit differently. It turns out that there are some shorthands for a lot of colors in PyPlot. One is that black is just the letter K. I think because black ends with a K, so and that's a pretty unique letter for colors. And so that's why I think they coded it as K, just to show you that it works. And then we probably should make sure that, let's see, that all of these make sense. Number bins. Yeah, you know what? Let's run it. Let's see what it looks like. Okay, cross your fingers with any luck. There it is. All right, so let's see. I don't love it. There it is. I think a line left looks better because I rolled 1, 1, or I rolled, whatever, 170 ones, 176 twos. Yeah, that's going to look better. And then this isn't random numbers. This is frequency of dice rolls. And then I'll say number bins from 1 to 6, because those are the possible values of the roll of a die. And then frequency does make sense. Okay, so this is a graph of the frequency of dice rolls. And my number bins are from 1 to 6 because the faces of a die are 1 through 6. And I'm curious about something. I have bins from 1 through 7. I think bins from 1 to 6 is still going to work. No, yeah, it does cut it off. Okay, interesting. So I do need to change this 1 to 7 for my bins. Oh, and you know what? That makes sense. I have to allow this graph to go past 6. You can see that this bar is centered at 6, so I need the graph to have a little bit more space to the right, which is why I need the bins to go up to 7 here. All right, so there it is. This is the dice roll simulation sorted out. I'll leave the code here for a second so you can see it. I hope this was helpful, and when you guys are done with it, the easiest way to turn it in will be to go to File, Print Preview, and then you're going to go to Control P for print. You're going to save this thing as a PDF. And you can see sometimes these PDFs don't look great. What it really struggles with is, this array has 1,000 items in it, but it's the best we're going to be able to do. And then you're going to save this as a PDF. And you'll throw it into your Python folder. And that's the file that you're going to turn in. Now, if you have any questions about how to work on these notebooks from home, again, let me remind you that all you would need to do is go to Anaconda's website, go to download, and you're going to download and install Anaconda at home. And then the only other thing you need to do is put your Python notebook, your IPython notebook, into whatever your root folder is at home, and you should be good to go. All right, guys, it looks like converting to a PDF here has kind of frozen my browser, so I think I'm going to end the video here, but thank you guys so much for tuning in, and good luck.